Yes, sir.
Okay, last time I did this problem, hydrogen atom. So there was a mistake in this one. So hydrogen atom is in ground state, excited by the radiation. Hydrogen atom is excited by this using this radiation. Okay, so because of this radiation, so this radiation will correspond to energy of h nu. So that frequency nu is c by lambda. Okay, so this energy is the energy corresponding to the jump from the ground state to the final state. Okay, so this delta E, using this value of 975, will get us 12.75. Okay, it's a straightforward calculation only. Okay, it should code electron volts. First, we'll get in joules. Okay, because we are going to use that formula 13.6 by n square. So that is in electron volts. So to convert it into electron volts, divide by 1.6 into 10 to the minus 19. Okay, calculation is there. So from that we get the delta E as 12.75. Okay, so that delta is 13.6 by n square minus. So final energy is minus 13.6 by n f square. Initial energy is minus 13.6 by 1 square. That should be equal to 12.25, 12.75. So the final is the higher energy, and the ground state is here. So when you subtract the energy of this level minus this level, you will get a positive point. So this is at a higher level. Okay, so it is plus 12.75. So from this I get minus 1 by n of square as this one. So last time I did the mistake here. I put this as plus. Okay, so from that you'll get as 0.60625. So that is 0.25 square. So from this I'll get NF as 4. So this is fourth level. So after reaching the fourth level, the electron can drop down to other levels, lower levels to give the radiation. So the number of spectral is resulting. Okay, first this radiation is given to excite to a higher level. After that, it's allowed to fall down. So because of it falling down, it will emit lines. So how many lines it will emit? So from the fourth, this thing, if it drops down to lower levels, 1, 2, 3, how many lines it will emit? How did you get that? So basically, so you have to choose 2 lines, right? There is 6 lines. So answer is option C. Yes. Okay. Right. So we understood the steps now.
Yes, sir.
Find delta E corresponding to this radiation. So that will be equal to. So this delta E from higher to lower, it will be a positive point. Because higher, it's at a higher end. It's minus 13.6 by n square. So the outer one will be less negative. The inner one will be more negative. So from outer minus inner will be a positive point. Okay. The outer energy is minus inner square. Inner is 13.6 by 1 square. Right. So today we'll do nuclear physics. This is the content: atomic mass, composition of the nucleus, size of the nucleus, mass, energy, and so on, radioactivity. Okay, so to measure the mass of the nucleus, so we are using a unit for mass. So you know this unit, right? What is this thing called?
Atomic mass.
Yeah. So that's this. What is mass of one carbon atom? What is this 12 indicate? C is carbon. So what does this 12 indicate?
Isotope of the carbon. Mass number.
Yeah. So what is that thing? Number of electrons?
Plus Neutron.
Which is 6 protons,
Neutron plus
6 electrons. Mass is basically contributed by proton and neutron. Electron is mass is very less. Okay, and this is mass number. So mass basically comes from proton and neutron. So 6 mass of one single atom is 6 times mass of proton plus 6 times mass of neutron. Is that right? Divided by 12.
Yes, sir.
Is anything is missing?
Okay.
In a carbon atom, anything else is other than proton and neutron?
No, sir. No, sir. Mass of. Why did you include that?
It's an atom.
Okay.
It's easy to measure mass of an atom rather than a mass of a nucleus. In order to do that, you have to strip the electrons, right? You don't do the extra work. So it's mass of 6 protons, 6 neutrons, and 6 electrons divided by 12. So this is approximately equal to what?
1.67 into 10 power minus 27.
That is fine. But can we say this is approximately mass of 1 proton? See, mass of
Approximately.
yeah, approximately.
Approximately, okay. But mass of neutron is greater than that of proton.
Yeah. So in that approximation, I'm just trying to get an idea.
Neutron almost equal. Okay, sir.
And it's also approximately equal to mass of neutron.
Yes, sir. But electron it will be lesser, no, sir.
Electron is much less.
Okay.
It's a factor of 1,800. Mass of electron is 1,800 times
Greater than that of electron.
1 by 1,800 times mass of proton. This into mass of proton is mass of electron. So mass of electron is very small. Okay, so 1 atomic mass unit is approximately mass of 1 proton, and it's also approximately mass of 1 neutron. And neutron is slightly heavier than proton. Okay, so you can find mass of a carbon atom by using some experiments. Okay, that divided by 12 is approximately this one. So this is approximately, so basically you get a measure of how much. So basically mass of something you are measuring in terms of some unit mass. Okay, and this unit mass is approximately equal to mass of proton or mass of neutron. Okay, suppose if you say mass of carbon 12 is 12, that means its mass is approximately 12 times the mass of proton or 12 times the mass of neutron. Or you can say number of neutrons is 12. Mass of C12 in terms of atomic mass unit is how much? Mass of C12 is how much in terms of atomic mass unit? Well, right, this is the definition. That's what this statement means.
Yes, sir.
Numerator is the one I have here, mass of C12. That is 12 times atomic mass unit. So 12 EMU or whatever. Okay, so similarly, mass of oxygen is 8, no? 8 electrons. So what is mass of oxygen?
15 grams. Sorry, 15 AM.
Oxygen is 16, no? Yeah. So approximately 16 EMU. Okay. This will be exact, but other things will be approximate. We'll come to know why. Okay, so Z is number of electrons. Since the atom is neutral, it is same as number of protons. Okay, and this is not used that much. Capital N is neutron number. Okay, and mass number is Z plus N, number of protons plus number of neutrons. So basically, this will only the protons and neutrons will contribute to the mass. So that is why the sum of protons and neutrons is called the mass number. Electrons are approximately neglected for mass. and size of the nucleus. How can you relate the size of, let's assume size of proton, let me call it volume of proton and volume of neutron. Are they approximately same?
Volume of proton and volume of neutron.
Okay, let's say it's approximately same. It is true. Okay, so size of nucleus, how to relate to volume of proton and volume of neutron? It will get added, no? It's simple. It will be number of protons, that is Z. Plus E minus Z neutrons, right? So, and right. So let me assume that this is also true. Radius of proton is approximately same as radius of neutron. Okay. So this thing is approximately the mass number A times 4 by 3 pi radius of proton cube. Okay. So and volume of nucleon is 4 by 3 radius of nucleus cube. Okay, so from this I'll get an idea of what should be the radius of the nucleus. So radius of nucleus is how much?
Atomic mass times radius of the proton.
No, from this expression, just from this. Radius of nucleus is A raised to the power 1 by 3, right?
Okay.
So that's what is given here. So radius of the nucleus will go as mass number raised to the power 1 by 3 into some constant, and R0 is the radius of one nucleon. Because when A is 1, okay, 1 raised to the 1 by 3 is 1. So this is approximately radius of proton or neutron. There is 1.2 into 10 minus 15 meter, 1.2 Fermi. 10 minus 15 meter is 1 Fermi. Okay. So this is the important. The radius of the nucleus will go as A raised to the power 1 by 3. Okay, so if the nucleus has got Z protons and then A minus Z neutrons, right?
Yes, sir.
So the mass of the nucleus is Z times Mp plus A minus Z times Mn. Okay, because this is a constant. But the actual mass of the nucleus is capital M. This one, this term. Okay, so the difference is called mass defect. Like some mass is missing. Okay, if you have one proton or one neutron individually, the sum of the total is mass of proton plus mass of neutron. But suppose you bring them together and form a nucleus, like in helium. Helium is just one, no, not helium. Deuterium, right? Yeah, deuterium. There's got one proton, one neutron. When I combine that and make it a nucleus, its mass is slightly less than mass of proton plus mass of neutron. Okay, that difference is called mass defect. It's always defect in the sense the mass is reduced. Okay, so that, and we can relate mass to energy by this relation E equal to mc square. Where here the mass is delta M. Okay, so some mass has been converted into energy. You can think like that. Okay, and it is stored inside the nucleus, and this is the energy which we get, which we can use in nuclear reactions. Okay, and so there are here a number of nucleons, right? So to get binding energy per nucleon, this is the mass defect of the total nucleus, and this is called binding energy. And this energy is binding the thing, and this binding energy per nucleon is this divided by A, where A is the total number of protons and neutrons. Is also clear?
Yes, sir.
So this is binding energy per nucleon of different nucleus. So it will start from one. One is hydrogen, which has got one proton, and next to that will be hydrogen 3, 1 proton plus 1 neutron. Okay, similar different atoms. For example, oxygen 16, right? So it will be here. 25 is this one, so 16 will be somewhere here. That corresponding oxygen. And this is binding energy per nucleon. So it should be approximately constant because it's not total binding energy, it's binding energy per nucleon. So whatever is the binding energy of iron divided by 56, this is y-axis. What it with the mass iron is some delta m, that delta m divided by delta m c square is the binding energy, that divided by 56 is the binding energy per nucleon. That is in the y-axis. So ideally we would expect this to be constant, but there is some variation, and this is the variation which we can use in nuclear reaction. Okay, so let me give some understanding of this nucleus thing. See, nucleus, there are nucleons, right? It can be either proton, neutron, and let me assume there is some attractive force between them, right? So it's like a spring that is there. Let me say this is a proton and this is a neutron. Okay. Suppose the spring is compressed. The proton is there, and there is some energy here, right?
Yes, sir.
This energy corresponds to the binding energy. Okay, so when I'm converting this nucleus to this nucleus where the spring is relaxed, I can get some energy out. Okay, if it is fully relaxed means the full EB will come out. Suppose if this is binding energy, say EB2, and this is EB1. So then the energy that is coming out is the difference in the energy. Okay. Assume the normal state of the string is unstretched, relaxed state. When I'm forming a nucleus, I'm compressed. The spring gets compressed, so some form of energy is getting stored in the spring. Okay, that energy I can get released it. I can release it if the spring is relaxed. Okay, so here the binding energy of this, the one that is here, is less compared to the binding energy here. Okay, so suppose I'm converting the nucleus from here to here, that binding energy is reduced. Okay, so that reduction in binding energy will come out as energy. Similarly, if I'm converting a nucleus from here to the nucleus of this type, okay, then also energy will get released because binding energy is decreasing. Actually, binding energy is increasing, but this energy is actually negative. Okay, so if you actually draw in the conventional sense, this will be a U. Right now it's inverted U. To draw it with proper, this is actually negative values. It will become U. So it's like when you draw U versus X, okay, the system will be stable if the mass is getting occupied in this lowest energy position. This you know, right? This potential energy of a system, say with some separation R. Okay, suppose the system is at this point, it will try to come to the stable position. Minimum energy position is stable position. So when doing that, it will lose some energy, and that energy will come out. So this is actually U curve, inverted U. It's actually negative values. So the correct curve is inverted U. So this is the basic thing. So if you take a uranium nucleus and split it into nucleus of smaller mass number, that will correspond to this point. So when during fission reaction, the uranium nucleus will get converted to some nucleus of this type. So during this thing, there will be emission of energy. Similarly, during fusion reaction, when I take lighter nuclei and combine to get a heavier nuclei, there is a reduction in the energy. So it will come out as energy output. So this is what is happening in nuclear fission and nuclear fusion. So if you take a heavier nucleus like uranium-238 and convert it into a lower mass number nucleus, so there will be energy emission. Similarly, if you take a lighter nucleus like hydrogen, helium, something like that, and fuse it to a higher mass number nucleus in this range, then also there will be energy coming out. And that is nuclear fusion reaction. The nuclear force is what is nuclear force?
Force between the nucleons and the electrons, or force between protons and neutrons.
Yeah, whatever is there inside the nucleus. Inside the nucleus, there are protons and neutrons. Okay, so it is force between this proton and another proton, or force between proton and neutron, or it can be force between neutron and another neutron. Okay, so these are forces. Okay, so this force is dependent on distance. So if the distance is large, then there is some force, and when the distance is smaller, then the nature of force. So this is potential energy U. Okay, and this is the distance R. So what can you say force at this region for this corresponding value of R? What can you say about force compared to the force here?
It decreases. It is lesser.
Potential energy decreases. What about force?
Okay.
Force is positive, sorry, negative. Is that right? And this force is positive.
So I don't get it.
How is
Okay. Based on that minus dou U by the
force is related to potential energy is what?
minus dou U by dou X.
Okay, and here slope is positive, so force is negative. Here slope is negative, so force is positive. Okay, force negative means the force is towards minus r cap, because force is this thing into r cap, right? If you want to write in vector form, this may not have studied, but this is what it means. So force negative is towards minus r cap, and this force positive means the direction of force is towards r cap. Okay, so what is the meaning of that? So if the nucleons separation is this much, so since this force is towards minus r cap, the distance between the nucleons will reduce. It will try to see there are two nucleons. One is at the origin, okay, and this is at r. The direction of r vector is this one, right? In r cap. Okay, so when this separation is beyond some value r naught, the force is towards minus r cap, so it's attractive. Got it?
Okay.
Okay.
Yes, sir.
And when it comes closer beyond this r naught, okay, the force is towards r cap, so it will repel. If it comes too close, it will repel. So at a particular distance r naught, what is the force value here at r equal to r naught?
Yeah.
That is the stable point, stable equilibrium point. Okay, so this is the nature of the nuclear force. If you have two nucleons, it can be the proton or neutron or neutron and neutron or neutron and proton, doesn't matter. Okay, so if they are far apart at a distance greater than r naught, you will try to bring them closer. Okay, but if you try to bring it closer than r naught, it will start repelling. Okay, so the stable position is r naught. So if two nucleons are at a distance of r naught, they are happy. Okay, so they won't allow to go beyond that. They won't allow to come closer than that.
So, but system always need to reduce its potential energy in the nature.
Yeah, so this is the minimum potential energy point. R equal to r naught, that is the minimum potential energy point. You cannot use this potential energy of electrostatics where it is Q1, Q2 by R. Okay, this is classical.
Okay.
Modern physics. That is applicable only for electrons from outside.
Okay, sir.
This is the difference between classical physics and modern physics. Once you get closer and closer, it becomes what? Quantum physics. Okay, so that's why nuclear physics is a fundamental physics, which is different from other forces, like electrostatic force. So the rules applicable for electrostatics and Newtonian mechanics, Newton laws of motion, those things are not applicable. You get closer and closer to the nucleus, inside the nucleus.
Oh, okay, sir.
Okay. So this is called modern physics, which is different from those things. Okay, but if you take say a positive thing like what do you say, some charge q1 and this second charge q2, say q2 is negative and q1 is positive. Okay, this thing, the potential energy is this way. Sorry, q1 q2 by r square, it's minus, right? Yeah, so it'll be like this. So force is always towards minus r cap. So the distance will keep on reducing up to 0. So this thing will come closer and closer without any problem. Okay, but in the case of nucleus, in case of two nucleons, this is the nature of the force. It will allow you to come up to r0. If you try to come closer than r0, you try to push you out. Okay, so the stable position is the distance r0.
Yes, sir.
So radioactivity. What do you mean by radioactivity?
The
Some-
nucleon will emit some energy.
Okay, basically, it means some radiation is coming out.
Okay.
Okay. Radio comes from radiation. What is a radiation?
Energy.
Yeah, H nu. Energy in form of electromagnetic waves. That's important. Okay. Energy in terms of electromagnetic waves, and the energy of electromagnetic is H nu. Okay. So some radiation will come out. So in chemical reactions, if we take carbon and burn it, it will become carbon and oxygen atom will come together, right, and form a unit. In chemical reaction, if we take carbon and oxygen, okay, so this will form CO2, right? What this basically means is initially there was carbon separately, oxygen separately. After the chemical reaction, it will form one single unit of CO2. Usually they were separate. Okay, once it forms CO2, CO2 will become one unit. There is some bonding between C and O2s. Is that clear?
Yes, sir.
So similarly, in nuclear reaction is everything inside the nucleus. These things are all easy to create in the lab. But nuclear reactions means I'm going to do something with the nucleus. So if you take nucleus of some atom, it has got some number of protons and some number of neutrons. I try to do something and I can break it into say 2 nucleons with some different number of protons and neutrons and some P2 and N2. Okay, so when this sort of thing happens, there is a mass defect here, right? When you combine proton neutron to form a nucleus, there is some mass defect associated. Okay, here also within this nucleus there will be some different mass defect. Okay, here also some different mass defect. Okay, so if there is a difference in mass defects, then the difference will come out as energy.
So del M equal to del M1 plus del M2 only, sir.
No, in that case,
No.
that's what is happening here, right? See, when I take that is what binding energy per nucleon is not ideally it should be same for simplistically it should be same for all nucleus. Okay, but for different nucleus like uranium nucleus, this ion, the binding energy per nucleon is changing. Okay, so suppose you take uranium-230 and break it into some two smaller nucleus of this range. In that case, the binding energy of this thing has reduced. Binding energy reduced means the mass defect has reduced. Because binding energy is basically mass defect by c square. Right? Or mass defect into c square. So binding energy reduced means delta M corresponding to this new components is less.
Okay.
So suppose you take this iron, the difference between the 56 mass of 56 neutrons, some protons and neutrons, and compared to the actual mass of iron, that difference will be more for iron compared to uranium. Okay, put this simply, mass defect for uranium and these two elements here, the structure of this one will be different.
Yes, sir.
Okay, so when I'm doing this sort of reactions, in addition to this one, I can have an extra neutron here also. I can get an extra neutron here, or some extra protons or electrons also can come. because I'm splitting it, doesn't mean that I have to split it equally. Some extra protons and neutrons can come out. Okay. So when I'm doing this thing, I can get a alpha particle. Okay, so I can also get helium nucleus, which is 2 plus, that is 2 protons plus 2 neutrons. I can get a unit, okay, as this one, which is 2 protons plus 2 neutrons, that is called alpha decay, where one of the products is the helium nucleus, He24. This is not atom, this is a nucleus, because it's basically okay. Beta decay is these extra particles. Here I can also have electrons, and it can also be positron, E plus, okay. And the third type of extra thing I can get is, in addition to that, I can get some radiation energy, that is in terms of H2. Okay. So in addition of splitting the nucleus into two, I can get some smaller outputs also, like helium nucleus, or electron and positron, or it can be radiation, electromagnetic, just release of energy in terms of radiation. Okay. In addition to that, it can produce heat, which is basically the difference in the binding energy. And this is the one which is used in nuclear reaction. Okay, so basically there are mainly 3 types of products we are getting: alpha decay, beta decay, gamma decay. And why is this thing called alpha decay? The first one.
So the alpha particle is emitted.
Yeah. See, basically, in mathematics, if you want to say, let me take a variable, the first choice will be x, right?
Okay.
Okay. So the alpha is the first alphabet of Greek. Okay. So
your voice is very low, sir.
How come? Is it okay now?
Yes, sir.
Okay, just a little bit far away from the mic. Okay, so the first alphabet of Greek is alpha. Okay, so you are getting some initially when they study, you don't know what it is. Okay, only later they find out it's a helium nucleus. So whatever is coming, the first variable is alpha. Okay. Second type of variable alpha is beta. Third is gamma. So that is the actual reason for why this is called alpha beta. Okay. Similarly, X-rays. Why are they called X-rays? Not Y rays, Z rays, A ray, B ray. Because first time when they observed it, they did not know what it was. So they knew it was something unknown. So just like an unknown variable, you call it max as X. So unknown radiation, you just call it X. After that, the name got stuck for historical reason. Okay. So this is why X-rays are called X-rays. X-ray is basically electromagnetic radiation, HDU. Okay. When they first observed it, they did not know what it was. So they just named it as X. So that's why you call X-rays. Similarly, these radioactivity, whatever product you get, since you don't know what they are before studying them, you just called it first one as alpha, second one as beta, and third one as gamma. Because alpha, beta, gamma is the alphabet sequence in Greek. Okay. So what is a positron?
The opposite to the charge of electron, but the mass is similar to the electron.
So what is the difference between proton and positron?
Mass.
Yeah, charge is same. So positron is similar to electron. And where do you find positron? Where do you find proton?
Proton in the nucleus.
Okay.
Positron, I have no idea about it.
Positron basically you will get when you take the nucleus and split it. These byproducts are coming up, right? Other big nucleuses. So they will get. So it's as if it's within the nucleus only.
Okay.
Okay, it's as if a new particle has been created. It was there inside nucleus it was inside proton or neutron. Under the nuclear action, this particle has come out. Okay, so these are fundamental. Okay, you don't need to know much about this. So basically, you should know it comes from nuclear reaction. So you can consider it as a part of the proton and neutron. Okay, so radioactive decays. Radioactivity is basically the nuclear reaction, where I take one nucleus and split it into two, and in addition to that, I get some small products also. So radioactive decay. Why is it called decay? It's not called radioactive reaction. It's called decay. Chemical reaction, you call it as chemical reaction, right? You don't call it chemical decay or chemical growth. Okay, but in radioactivity, we call it as decay because basically, in general, it's like a bigger nucleus is being split into two. Okay, in some sense, it's like a decay. Or if you take the reactants, which is the so the reactant population will keep going down with time. As time increases, large number of reactant nucleus will get converted into product nucleus. So if you take the population of the reactant nucleus, it is decaying, right?
Yes, sir.
Okay, that's true in chemical reaction also. From reactant to product, the reactants will keep going down. Moles of the reactants will keep going down as the chemical reaction progresses. Okay, so reactivity means the number of reactant nuclei, it's capital N. So as time progresses, it will go down, right? So the rate at which the number of radioactive nuclei, capital N, is going down, that is dN by dt, right? Or delta N by delta T. That is proportional to N. You should have some understanding. Why is this so? If there are 100 nucleus, which is undergoing nuclear reaction, okay, so the number delta N, suppose I have another condition in which there are 50 nucleus, which is going this nuclear reaction. Here the number of reduction in the reactants after some time, and the number of reduction in the reactants after some time, here it will be more, right? Suppose here it has become 100 to 80, and here it will become 50 to 40, right?
Okay.
Okay, so here delta N is 20, here delta N is 10, right? Delta N is the number changed or number decayed. 50 to 40 is 10, no? And 100 to 80. So delta N is proportional to the population N, or you can say even delta N by delta T, because I'm measuring for a particular amount of time delta T, same amount of time delta T. So delta N by delta T is proportional to N. Okay, so this proportionally constant, I can call it as lambda. Okay, so for a small time interval, it becomes dN by dt. And as time increases, delta N will decrease.
Yes, sir.
Okay, so that's why you have to put a negative sign here, minus delta N by dt. So dN by dt is minus lambda N. So this you can integrate to get this one. So initially at time t equal to 0, the number of nuclei is not. If you put t equal to 0, this will become 1, right? So at time t, so after time keeps increasing, it will keep on decreasing. So when will n become 0?
A time infinity, sir.
It will take a very, very long time to completely, actually it will take infinite time. So this is the nature of the graph. So if it started 100 nuclei, it will become 50, just keep on reducing, but to reduce it completely, it will take infinite time. So this is law of radioactive decay. It basically says how n goes down with time. Okay, so it basically based on only one understanding, delta N by delta T, the rate at which going is pushed to N. Okay, so an analogous situation is suppose you take population of a country or world. So dN by dt then is proportional to population, right? Because if 100 people are there, then the number of new people will be more, right, compared to 50 people.
Yes, sir.
This is the rate of growth of population is proportional to the current population. Okay, but here it is plus because as time increases, P will increase. Here I have to put this minus N because here it's decay. Here it is growth. population growth. This is also like a decay of population only because of radioactivity or radioactive reaction. Okay, so here the decay rate I'm defining a new quantity. It's dn by dt, and since dn by dt is negative, I'm putting a negative sign here to get this as a positive quantity. Okay, so decay is also important term to remember. So from this, I have already found n as n naught into e raised to the power minus lambda t. So using that thing, I'll decay here as lambda n naught into e raised to the power minus lambda t. Lambda is constant. Okay, so lambda is basically how steep this thing is going down. So if lambda is more, means it will become like this. Okay, suppose I call this lambda 1, and this is lambda 2. This means the lambda 2 is greater than lambda 1. Okay, so I can have some other lambda like this. So lambda is basically saying how fast the thing is going down. It will be different for different nucleus. And since it is fixed for a given nucleus type, and A naught is the initial number of nuclei, so these two I can combine as R. Basically, if you remember this one, it's enough. And we have to remember this one. And half-life is the amount of time taken for the population. Suppose the initial population, that is number of nucleus is n naught. So after t half, what will be the number of nucleus remaining on the reactant side? After t half, n naught will keep reducing, right? So after t half, how much it have reduced?
n naught by 2.
So whatever time it takes to reduce by n naught by 2, I call that time as t half.
Yes, sir.
And you have the solution n naught into e raised to the power minus lambda t. Okay, so n half, let me call it. So half-life, let me call that tau.
Sir, is that n doesn't mean that the amount of DNA undergone decay or amount of DNA at present?
See, reactant nucleus is known. If you get like this, the number of reactant nucleus is known at time t equals 0. So here is the number of nuclei which is just still not decayed. It's on the reactant.
Okay.
So, and this is n naught by 2, right? Definition. Because at time tau, there is a half-life. Population is reduced by. From this, I'll get e raised to the power.
So lambda means that is constant.
Yeah, it depends on the nucleus type. So here it is. So 2 will become e raised to the power lambda tau. So if you take log on both the sides, lambda tau is ln 2. So half-life tau is ln 2 divided by lambda. That's what is here. And you have to remember this also, 0.693. Okay, so half-life is this one. So the initial number of nucleons on the reactant side is 100. So to reduce it to 50, it will take some time, say half-life of say 1 day. Okay, so in next one more day, what will be the number of nucleons here or nucleus? 25. Okay, so even after one more day, it will become 12.5. On average, okay, because it doesn't make sense to have 0.5. So on an average, it will become 12.5. Alpha decay. So this is a reactant nucleus of Z is the number of protons, and E is the mass number, which is protons plus neutrons. So it will get converted into a smaller nucleus where the number of protons are reduced by 2, and number of nucleons have reduced by 4. So basically, it has lost 2 neutrons and 2 protons, and that has come out separately as a single unit, and 2 protons and 2 neutrons is a single nuclear unit is a helium. Okay. Okay, and this particle, when they first saw it, they did not know what it was. So we just called it alpha. So that's why it's called alpha particle. And this reaction is called alpha decay. In the sense, its size of the nucleus is reducing, right? And also we can say the number of reactant nuclei is going down, and there will be a mass defect. So mass of this thing. So the initial mass is mx, mass of this nucleus. Final mass is the mass of this nucleus plus the mass of this nucleus. So there is a difference. So there is loss of mass. There is a loss of mass, and that corresponding energy is into c square. So this energy will come out when the new nucleus goes undergoes this reaction. Similarly, in beta decay, it will emit an electron. Electron is also called beta minus. The process in which the electron is getting emitted is called beta minus decay. Minus is basically representing it's an electron, it's a negative sign, and positron can be also emit positron. So it's called beta plus decay. So this is the nucleus, phosphorus 1532. Okay, so it's getting converted to 1632 sulfur. In addition to that, I'm getting an electron and an antineutrino. This is also some fundamental particle. Neutrino is new, antineutrino is new bar. Okay. You don't have to know all these things, you just have to know something is happening. Because of that, there will be reduction in the mass, and when there is reduction in the mass, there will be generation of energy. So this is an example of beta minus decay, in the sense electron is coming out. Similarly, I can have a reaction in which the positron is.
So there mass increase, Nisha, 15 changed to 16.
No, that's what I'm saying. See, when you consider this as mass of 16 protons plus 16 neutrons, then it will be different. But 16 protons and 16 neutrons are forming a nucleus, its mass will be less than when they are individually as individual units. That is the original concept. No, when I have Z protons and A minus Z neutrons as separate quantities or separate entities, it will have a total mass of this one. Okay, but when I combine them and make it a nucleus, its mass is m. Okay, but when I'm combining different nucleuses, the amount of mass difference is different. Okay, so here, see, here there are 32 nucleons, here also 32 nucleons, right? So you might think the mass of this one and this one should be same. But when this forming this sort of a nucleus, there will be loss of mass defect. Here is more for this thing, sulfur. Okay, and that mass defect, and even if you include this mass of this and this, still there will be mass of this reactant will be more, could be more. Okay, so this is a basic interesting thing of this nuclear reaction. When you have two protons separately, their total mass is 2 times mass of proton, but you are bringing them together, the mass will be less, could be less. Okay, and that reduction in mass is getting converted to energy, and that energy is called binding energy. That I gave a model. Think it's of it as a spring. Okay, so mass of this thing is not just mass of proton plus neutron. It could be different from mass of these two, and the difference in the mass will get stored in this spring energy. Okay, so if the spring is getting more compressed, means the binding energy has increased, so the mass defect will increase. Okay, so when proton and neutron are forming a system like this, the mass of this part is not mass of proton; it's less than that. Okay. This is the idea of mass defect. So again, this is all modern physics. You do not think classically. Classically, it's like conservation of mass, right?
Okay.
Here, conservation of mass is not valid. So this is what is modern physics.
Okay.
So here, in some sense, you can say energy plus mass is conserved. Whatever mass is disappearing, it is in form of this energy, spring energy.
Okay.
Right. So beta decay. So this is an example of beta plus. The first one is an example of beta plus decay, and the second one is an example of beta plus decay. Okay, so right. Okay, so in this this you can consider final step, but what is actually happening is uh, one neutron here. So if you see this thing on the left side, it's 15 protons, right? Here it has
Okay.
15 protons, but the number of neutrons is same. So basically, what is happening is one neutron is getting converted into one proton.
Okay.
So, and that is the reaction here. Neutron you can convert as proton plus electron plus antineutrino. Okay, so this way the charge on the reactant side, which is neutral, and the charge on the product side, which is proton plus electron, both are neutral. Charge is conserved. Neutrino is just doesn't have any charge. Neutrino or antineutrino doesn't have any charge. So the charge and electron charge are right are balanced here. Okay. Similarly, for in this beta plus decay, 11 protons, here it is 10 protons. So proton is disappearing and has become proton is getting converted into neutron. Here is other way. Proton has increased. So neutron is getting converted to proton. Here proton has decreased, but then the mass number is same. So proton is getting converted into neutron. So this is the basic reaction. Proton is getting converted into neutron plus positron plus neutrino. Okay, this is our final step. This is the in-between step. Okay.
Okay.
Free neutron reduces with proton. The DO proton to neutron. So all this conversion of this converting neutron into proton plus electron, all this are part of nuclear reaction. It can happen only within the nucleus. Okay. And so this is beta decay. And finally, we have gamma decay. So gamma decay is just electromagnetic radiation coming out. So suppose you have this nucleus, cobalt 2760, and converted into nickel 2860. So number of protons have increased by 1, and neutron is decreased. So in this thing, so this is emission of beta minus. So beta minus will bring it here, and after that, it will emit some radiation to get down to this level, and one more radiation to get down to this level. So this is like energy levels of an electron, but this is actually energy levels of nucleons. Okay. So one way to figure out this is the energy difference is very high, mega electron volts. In terms of electron energy levels, it's in terms of what unit? Minus 13.6 by n square, that 13.6 electron volts, right?
Yes, sir.
Here it is mega electron volts. So you can see the difference, energy difference between the levels.
Yes, sir.
So nuclear energy has got nucleus has got higher energy capability. So in fission reaction, I take a nucleus which is called heavy nucleus because the number of neutrons is more, like uranium 92 235, and see this uranium 92 235 as a nucleus, it will in general be stable. But when I try to introduce a neutron into this nucleus, okay, then it will become unstable, and it will try to, okay, once I put in this electron, the number of protons is same, and it's going to add to the number of neutrons. It becomes 236. Once it becomes like this, it will become an unstable system, and it will break down into two smaller nucleus, barium 56 and krypton 36. So 56 plus 36 is 80, 84. Sorry, 92, right? 18, 92. Okay, and then 144, 89. It's how much? 144 plus 92. Okay, it's less than 236 by 3. Okay, so that 3 is coming from this 3 neutrons. Okay, so if you look at this left and right side, the number of protons and number of, okay, basically the mass will be conserved. Mass in the number of nucleons, Okay, the same reaction can produce other pair of intermediate mass fragments. So neutron plus uranium-235 plus. Okay. So after the neutron enters this one, this reaction is also possible. The uranium-236, it can also split as these two with 4 neutrons. It's also split as this one without going into this intermediate step. Okay, so it depends on how many uranium will get converted to the first reaction, second and third. Okay, the basic thing is if we take the mass of this one, the product side, mass of this nucleus, we don't take this as mass of the individual nucleus. Once it forms a nucleus, there will be some mass defect. So mass of this 4 nucleus plus mass of this one plus mass of this one, that will be less compared to this one. Okay, that mass binding in difference the binding, and that will come out as energy. So in nuclear reactor, you take this sort of a radioactive nuclide, uranium-238. So when it captures is high, so this one is getting converted into uranium-238 which captures neutron, and then converted to this one, and this one is getting split into. This one is getting converted. So when this sort of nuclear reaction goes on, basically it corresponds to this curve only. You start with the reactant of this particular binding energy. The product will have binding energy at this level. Okay, so this difference in binding energy is the one which is getting released as nuclear energy. Okay, so this is a fission reaction where a heavier nucleus is getting broken into smaller nucleus. In nuclear reactor, this same thing is happening. So this is the picture. So you have a uranium-235, okay, and you take a neutron, and see if you just leave this uranium-230, it will be in a stable state. But once I introduce this neutron, it will become unstable and will split into 2 nucleus. And when it's split into 2 nucleus, the mass difference between these two will come out as energy. Okay. This okay, when it releases energy, in addition to 2 nucleus, it also releases 3 neutrons.
Okay.
This one. So these 3 neutrons will go and attack some other. This is one uranium nucleus, uranium-235. It will go and attack some other uranium-235. So since 3 of them are there, you go and attack 3 of them. Okay, and each one will produce 1 fission. Okay, and each fission, this thing will create 3. So we can say this is 1 unit. It's splitting into 2. Or I can consider this one. This one is 1 unit. Okay, and the same thing is repeating here, splitting into 2 and 3 neutrons. So at this level, I have 1 splitting, and here I have 3. Okay, so at this next level, I have how many? This sort of units?
20.
9.
Okay, 9, 27 neutrons and 9.
Because there are 3 neutrons, no, here, 3 here, and 3 here. Each neutron will go on split 1 uranium-235. Here there are 3 neutrons, so we'll go and split 3 of the uranium-235. At this, there are 9. We'll go and hit 9. Next will be 3 cube. Okay, so this whole thing will release a lot of energy, and the whole thing will produce huge amount of energy and will result in atom bomb. But in a nuclear reactor, what I will do is I will absorb
excess neutrons.
Yeah, instead of at this stage, I'll absorb these 2 neutrons because I don't want too much of energy. The reactor will explode. So I'll absorb these 2 electrons. Only 1 neutron will go and hit this one, and whatever neutron is getting created, I'll just absorb. So this way, at any stage, the number of nuclear fission happening is 1. Okay, so this way the energy is controlled. So that becomes a nuclear reactor. It is controlled. Clear?
Yes, sir.
So that control is happening because it's control rods. The job of the control rod is to absorb the neutrons. Uranium will get split. When it splits, it will produce 3 neutrons. I have to absorb 2 neutrons. So that job is done with control rod. So if you insert the control rod more, it will absorb more neutrons. So this will produce energy, and that energy I use it to heat water, and that heated water is going to run this turbine to generate electricity. This is a schematic of a nuclear reactor, where the nuclear reaction happening is a controlled nuclear reaction. Fission will give energy, right? Similarly, I can fuse to give energy. So I have to take two hydrogen nucleus, fuse it together. See, this combining 2 hydrogen nucleus to produce this H12 nucleus, you cannot do in a lab. This is normal lab, where you can do chemical reactions. Okay, but these sort of things are nuclear reactions. It's either done inside a nuclear reactor or it's happened naturally. So if you take 2 hydrogen nucleus, bring them close together, it will form a nucleus like this with 1 proton and 1 neutron. Okay, so here basically. Say it again.
It is an example of beta plus decay.
No, beta plus is okay. You can say that because positron is getting created. Okay, let's see whether it's beta plus. So basically, what is happening here is 1 proton is getting converted to 1 neutron.
Okay.
Left hand side there is 2 protons. Right hand side there is 1 proton and 1 neutron. So basically, 1 proton has got converted to 1 neutron. So I think it's same as the beta plus decay only. Beta plus decay proton is getting converted to neutron, right? Yeah, it is same. Okay, and then this is isotope of hydrogen. This has got 1 proton and 1 neutron. 2 of them will combine to give helium, 2 protons and 1 neutron. Okay, plus a neutron plus this much of energy. So this energy corresponds to the difference in the mass. There is a difference in mass of this one, that difference is coming out as energy. So basically, the mass of these two is less compared to mass of this one, and the difference in mass is getting converted to energy. Okay, and then here, okay, here I've got helium 2, 3, and then okay, this is one way of combining these two. Another way of combining these two is okay, hydrogen 1, 3 is tritium plus the normal hydrogen plus this much of energy. Okay, nuclear fusion reaction. Okay, this is the one that happens in the star. So basically, to bring these two things close together, it's not possible in the lab, but one place where it happens naturally is in the star. Okay, so for example, in the star, 2 hydrogen will combine together. I think this is same as the first one, the previous one, yeah. And then the electron and positron and electron will combine to give gamma means radiation, H radiation plus some energy. Okay, and then H12 and H1 will combine to H23 plus some energy, and H23 plus H23. Okay, this is a stable nucleus. This is not a radioactive. In the sense, these things will not keep quiet. It will do some nuclear action. Once I get this He24, then further nuclear action will not happen because this is stable. Hydrogen is also stable. Okay, so this will be the last step. So here also there is release of energy. So in all the steps, some energy is getting released. So when I'm converting from here to here, so total amount of energy released will be the sum of all these 4 energies. And this full step of 4 reactions is called proton-proton cycle. Okay, for the fourth reaction, the first reaction must occur twice, in which case 2 light. Right. So any questions?
No, sir. No, sir.
Let us see whether we can solve some problems. So this is the first question. Radioactive nucleus x ZA undergoes spontaneous decay in the sequence P Z minus 1 C D. Z is atomic number of the element X, the possible decay of particles in the sequence. Alright. So basically, you should know what is alpha decay, what is beta decay, or beta minus decay, and what is beta plus decay. So to go from here to here, what is happening? Number of protons has reduced, no?
Yes, sir. Beta plus decay.
Okay. And from B to C,
Alpha decay.
2 protons are disappearing.
Yes, sir.
So alpha decay. And from C to D, proton has increased, right?
Yes, sir. So
So neutron.
neutron is
So which option is it?
beta plus. Option D.
This guy has given us C. The first one, the number of protons has gone down, right? So first one is beta plus decay. Proton has got converted to neutron, right?
Yes, sir.
Let me check. Proton has disappeared. Proton disappearing is beta plus.
Yes, sir. Yes, sir.
The first one is beta plus, the second one is alpha, and the third one is beta minus. Okay, so correct option C. It's clear, no?
Yes, sir.
So this is the basic thing. When you produce an electron, okay, you can remember like this. Since there is positive charge reduction, so this one should be positive. Reduction of proton means positive charge has come separately, no? So positron has come out. So that means it's beta plus D. So here the proton has increased, so the balance is I should have an electron here. So that 1 minus will cancel this plus 16 to give plus 15. So that way you can remember. Proton has reduced means E plus has come out.
Yes, sir.
This one half-life of radioactive nucleus is 100 hours. The fraction of original activity that will remain after 150 hours. Try this one. What is activity?
Rate of decay.
In terms of N?
dN by dt. Minus dN by dt.
So JMT is negative. So this is activity. So half-life is 100 hours. Once you know half-life, what I can know? Half-life will give me what?
Lambda value, sir.
So basically I have to find R at 150 hours, right? So this is the fraction. So I have to find R divided by R naught. So this is R naught d raised to power minus lambda t, right?
Minus e power minus 0.63 value. How to calculate that answer?
No, basically you know lambda from here. Okay, and R is same as some constant d raised to power minus lambda t, right?
R naught is lambda only, no, sir. Lambda into n naught.
Yeah. Whatever it is, you can combine that as a full constant because he's asking fraction, so R naught will cancel. R at 150 hours divided by R naught. This is the thing I have to find out. That is same as e raised to the power minus 150 hours divided by e raised to the power lambda into c. Okay, so e raised to the power minus lambda 150 is this 100. Mathematics is involved. Got the answer?
No, we have another formula. Now I remember this one. A is equal to A naught by 2 power n.
Yeah, you
2
can use,
power 1 by 1 by 2 power 3 by 2, sir. Answer.
yeah, that is option
8 rupee. 1 by 8 rupee. Oh, God.
2 raised to the power 3 by 2 can write as 2 raised to the power 1.5, right? So that is 2 into 2 raised to the power half. That is 2 root 2.
Okay, 1 by 2 into 1 by 2. Okay. 1 by 2 root 2, sir. Yes, sir.
Option B.
Yes, sir.
This is the basic thing. R equal to R naught into e raised to the power minus lambda t. Basically, you have to find R by R naught. Because you have to find the fraction. Original activity is R naught. So R at 150 divided by R naught. That is e raised to the power minus lambda 150 hours.
Yes, sir.
This one, what happens to mass number, atomic number of the element? The devil's gamma.
It will remain unchanged.
What?
It will remain unchanged, sir.
Yeah, because this is just electromagnetic radiation, so nothing will change. Mass number, option B. Half-life, this one. The number of nuclei in the sample is this one. The activity of the sample is made. Okay. This is also straightforward. So we take rate at half-life.
So that 2 into 10 power 21. Is that initial number of nuclear remain after that radioactivity as well?
Take it as initial.
Initial.
Yes. Got it?
If you take it as n value only, you will get that value, sir.
You can take it as n naught. See, the way I have done is it clear?
N naught means then you won't get the answer, sir.
No, approximately no. So
No, if we consider that as n only, then I get that answer, sir.
see, what is the difference between n and n naught? It's half, no? It will become 1 into 10 is to 21. Okay. So order will not change.
But we don't know how many T it must have undergone. It could have been n by 16 or something like that.
Okay, see, this is what I've done. Rate is this one, right? Minus dn by dt. And n is a naught in e square minus lambda t. So if we differentiate this thing, I'll get lambda minus lambda. So minus it cancels. So it's a naught in this one, right? And rated, we have to find t half. Okay, half life. So I have to put t equal to t half. If we put t half, then it will become lambda, it will become 0.693. 0.693 is ln 2. So this is e raised to the power ln 2 raised to the power minus 1. So that is 2 raised to the power minus 1, that's half. So n naught into lambda into half. N naught is 2 into 10 is 21. Lambda is 0.673 divided by t half. That is 1.4 10 is 7. So this is the calculation I have to make. Okay. So 2.1 by 1.4 is 3 by 2, 7, 3, and then 7, 2. 3 by 2 into 0.693 is approximately 1. Okay, so it is 10 raised to 4. 21 minus 17 is 4. So this is the calculation I have done. Is it clear? If you try to remember too many formulas, you might get it wrong. I just use this formula, R equal to minus d by dt. This is basic formula, right? This is the definition of this activity. And n is n naught into e raised to minus lambda. So using that, I'll get this one. And I have to find the activity at this half life. So I have to put t equal to t half. So if when I put t equal to t half, lambda t is 0.693. Okay. After this, just calculation. Is it clear?
Okay. What did you do, sir, after that e power minus 0.693 equal to n naught lambda into half? Where did that e go?
0.693 is ln 2, right?
Okay, okay.
So it is e raised to the power minus ln 2. So this I can write as e raised to the power ln 2 minus 1.
Okay.
And this is 2, right? So this is e. So this is 2. So 2 raised to the power minus 1.
Yes, sir.
has become half.
Okay, sir. The value is half. Okay.
If you remember too many formulas, then you have to remember correctly. If you remember the basic, then it's easy to also making mistakes or less. So basically, I've used these two formulas. R is minus m, this basically definition of R, and this formula for half-life 0.693 by lambda, and 0.693 is ln 2. Three things I've used.
You said
This one, rate of disintegration, En by dt
N by N into
minus dn by dt.
2.3 number of atoms of
It's 10 raised to 10. Half-life is given. So basically, you have to find n naught, and that instance will be n naught by 2. So here, if you put n equal to n naught, become n naught into lambda d is equal minus lambda t. 10 raised to 10 is what? Okay, at half-life only. So lambda into t is 0.693. This is half. Okay. So n naught is 2 into 10 raised to 10 divided by lambda. Lambda is 0.693 into t half. So this is 4.4 by 6.3 into 10 raised to 90. It's 3 times, is it? It's approximately 0.7, right? 44 by 7. 7, 7, 6 times. So 6 times 10 is 90. Okay, here's one small catch. Basically, we have to find, this is not required. Basically, you have to find n naught into e raised to power minus lambda.
not into
You have to find the activity at a particular time. So that is n naught into e raised to power minus. So this is the thing we have to find.
that is N only, no, sir.
Yeah, you have to find n at that particular time. So this two factor will not come. So this will be 3 then. Yeah. This is at a particular time t. Okay. So you have to find n at that particular time. So at that particular time t, n is n naught into e raised to power minus lambda. This floating at a point. So what I have to find out is 10 raised to the power 10 divided by lambda. And lambda is 0.693 by t half. So from this I'll get this 3 into 10 raised to 9. Clear?
1 minute, sir. Thank you.
This step is clear, the first step.
Is the rest is clear only? Then calculation.
What you have to find out is n naught degrees from minus 1 because at that particular time. At an instant.
So 3.08 into 10 power 19.
So all the calculations you have to do approximate. Okay, so it's approximately 2.2 by 0.693. So it's 2.2 by 0.7. So it's 21 by 7. That is approximately 3. Okay, you don't have to do the exact calculation. Clear?
Yes, sir. Yes, sir. Approximately only 3.08, sir. Exact calculation 3.19.
See, one thing you can do this 10 to 19, right? So you can eliminate other things. You can figure out this approximately because it's 2.2 by 0.693. So it's approximately 2. It's approximately 2.1 by 0.7.
Okay, okay.
2.1 by 0.7 is 21 by 7. That is approximately 3.
Yes, sir.
Okay, so I have sent you a mail in which I sent the link for DPPs, PYQs. Did you check that?
Yes, sir. Just before the class only.
Yeah. So in that you solve problems. Because your more the number of problems you solve, it's better.
Yes, sir.
So you got your laptop. This is the link I've
Yes,
sent.
sir.
So chapter wise it is there. Chapter 1, chapter 2. You can either click PDF or HD. So the laptop is working. What about the journal software?
Yes, sir. I have downloaded that software, but I can't open that. Maha, you sent me, sir, that folder in that Google Drive.
Yeah, but you didn't ask that guy to install.
They told my father to ask by yourself.
Okay, fine. It's a Microsoft software only. It's on the Microsoft website only, so it should not be a problem. So just try to do that.
I have downloaded it. Sir.
Okay. Download means you just have double click. It will install.
I have installed it again.
Okay. So any other question? We close now.
No, sir.
Okay. Tomorrow is Friday, right? Okay. So tomorrow will be. So work energy power. I think some problems are there. No collisions are there. So I'll continue with work energy power. Okay. So how much? So basically, you have to practice problems. First, try these PYQs, and then after that, if you have time, you try these Akash model problems. And you have sent some snaps, no? So which topic is that?
Dual nature only, sir. Only one. Okay.
Okay.
Tomorrow I will send more.
Okay, fine. We'll meet tomorrow.
Bye, sir.
Bye.